Hello, everyone, and welcome. In today's interesting physics class, we are going to talk about the principle of homogeneity and how to use it in proving the dimensional consistency of equations of physical relations. We have a question right here before us, and we are asked to prove that this formula is dimensionally consistent. Before we begin, I want to walk you through very briefly on the concept of the principle of homogeneity. What does this mean? Well, the principle of homogeneity states that expressions on both sides of an equation of physical relation must be the same. If you look at this physical relation or equation, you will discover that there are two parts. Here we have the left-hand side, and on the other part, we have the right-hand side. Okay, so it is an equation because it has a left-hand side and a right-hand side. Now, based on this principle of homogeneity, it implies that what we have on the left must be equal to what we have on the right for this principle to hold true. Okay, now in a situation whereby we go on to prove that this equation is dimensionally consistent, but we arrive at different solutions. For example, if we arrive at a t on the left and arrive at something else on the right, it means that either we are wrong or the equation is not dimensionally correct. So that is what it means. So using this principle of homogeneity, we can go ahead and prove that t is truly equal to 2 pi multiplied by the square root of L over G. All right, before we go on to solve this very problem, we have to first of all identify the given variables in this equation. That should be your first step. Identify the given variables in the equation. So whenever you are solving problems on the principle of homogeneity, or if you're asked to prove that an equation or a formula is dimensionally correct or consistent, the first thing that you must do is to identify the given variables. Here we have t is equal to 2 pi multiplied by the square root of L over G. First and foremost, let's identify what we have here. T is equal to time, then 2 pi is dimensionless, okay? So whenever you're solving problems on dimensional analysis, you must understand that these numbers, let's say 3, 4, 5 pi, 2 pi, 4 pi, they don't have any dimension. So we say they are dimensionless. Okay, they have no dimension, so we say they're dimensionless. Then L is equal to length. Then the last one, G, is equal to acceleration due to gravity. Okay, now having identified all the given variables in this equation, what's the next thing that we are supposed to do? The next thing is to determine their respective dimensions. That's the next thing that we're going to do. But then we'll mostly work on the right-hand side because the left-hand side, which is a t, is already in its simplified form. So that means that we already have a clue on what our answer is going to look like when we prove that this equation is dimensionally correct. We're only going to work on the right-hand side. We'll try to simplify it to see if we'll get what we have on the left. If we are able to get what we have on the left, it means that the equation is correct. But if we don't, then there is a problem somewhere, either from us or from the equation. Now, using the MLT system, remember that we have 7 fundamental quantities, but when it comes to dimensional analysis at our level, we use MLT, which represents mass, length, and time. Okay, so the dimension for mass is known as capital letter M. The dimension for length is known as capital letter L. And the dimension for t, which is time, the dimension for time is known as capital letter T. So wherever we see mass, we put an M. Wherever we see length, we put L. And wherever we see time, we put capital letter T. That is how it works. Okay? So we're going to do the replacement when it is time. Now, having known this relationship, the next thing to do right now is to use it to determine their respective dimensions. Okay, so on the left-hand side, we have a t. This is time, right? What is the dimension for time? The dimension is just a t. Okay, because we know that time, this is capital letter T here, and it represents time, and the dimension for time is capital letter T, and that's all. Now for the length, remember I said that 2 pi is dimensionless, so we are not going to work with it. It's a dimensionless quantity or a constant. Now for the L here, the L here represents length, so L is equal to the dimension for length is just L, okay? It's just L. Now for the G, okay, the dimension for G can be determined through its units or through the definition. Now, how do I get this? From the definition, we say that acceleration is the rate of change of velocity with respect to time, or we can also use its units, okay, to determine its dimension. For example, G, the unit for G is meters per second square. So we can use this as well to determine its dimension. And I'm going to show you how that works. Okay, so let's get right into it as we try to do it together. Here we have that T is equal to 2 pi multiplied by the square root of L over G. Now, what's the next thing that I'm going to do here? I'm now going to rewrite this using what we call the fractional exponent law. Now, it says that whenever you have a square root of a number, for example, let's say the square root of a, this can be written as a to the power 1 over 2. Okay? When the number is in a square root form, you can change its outlook or the way it appears by writing it this way, that number raised to the power of half. So that means that I am going to rewrite the L and the G, since they are under one square root, as L to the power of half and G to the power of half. That's what we're going to do right now. Now let's do it. We have that T is equal to 2 pi. Then this is going to be multiplied by L to the power of 1 over 2. I believe you know why it's now to the power of 1 over 2. It's simply because it's under the square or inside the square root. Now this is all over G raised to the power of 1 over 2. Now, having done this, what's the next thing that we are going to do? Okay, so we have a law in according to the laws of exponents that says if you have something like a to the power, or let's say 1 over a, okay, 1 over a, it can be written as, remember that this a here has the power of 1 underneath, it can be written as a to the power negative 1. So here is what is happening here. If you have 1 over a to the power of 1, okay, you can move it from the denominator to the top, and when you move it from there, this number, which is a positive down here, now becomes a negative. It now becomes a to the power negative 1. Let's also take another example. For example, if you have 1 over a to the power 2. Remember that down here, the a is a positive number, right? If you decide to take it off from the denominator, it goes up and it's now going to become a to the power negative 2. So if it is a positive number down here, when it goes up, it's going to be a negative number. If it's a negative number down here, when it goes up, it's going to become a positive number. It is called the negative exponent rule. Okay? So with that right now, I'm going to remove this g from the denominator by taking it to the top. And remember what's going to happen to the power. The power is 1 over 2. And down here, it's a positive number. Now, when I take it from this denominator upwards, it's not going to be a negative number. Here is what's going to happen. We now have that t is equal to 2 pi, then multiplied by L to the power 1 over 2, then times G, okay, to the power negative 1 over 2. Okay, so once you remove it from the denominator, it's going to be multiplied by the one that's there already. In this case, we have L to the power of 1 over 2 there already. So once you take it, it's going to multiply it. And then it now becomes negative 1 over 2. It's called the negative exponent rule, okay? And this is very important. You need to know about it whenever you're simplifying expressions in dimensional analysis. Now, let's continue. We have here that t is equal to 2 pi L to the power 1 over 2, then multiplied by, remember that we did not get the dimension of, our G, we just got the units, okay? We just got the units, so we can now use the units to find the dimension. I'm also going to, since length is measured in meters, right? L is measured in meters. When we talk about length, we mean your distance, your displacement. It's always measured in meters. So length is measured in meters. And that means that wherever I see L, I'm going to replace it with M, which is meters. And then for this G here, I'm going to replace it with its own unit so that we can find that dimensions. Or alternatively, I can also use the dimension for length is still going to work, but we need to use the units for G to find its dimension, since I will say we don't know it for now. Now here, we're now going to have, I'm going to replace this G with meters per second square. I remember that the value of G, or G itself, is being raised to the power of negative half. So we now have negative 1 over 2. Okay. So now what's the next thing that we are going to do? I'm also going to rewrite this using the same negative exponent rule that says when you have a number down, or let's say you have something at the denominator, you can take it upwards, okay, but then the power becomes a negative. Hence, we're going to have t is equal to 2 pi, right? And here we have L to the power 1 over 2, then multiplied by, I'm just going to say this, multiplied by m, and then when this s squared goes up, it now becomes m slash s, or ms to the power negative 2. Okay? Now remember that all these are being raised to the power negative 1 over 2. All right. So it's not yet time for us to substitute, but we shall do that in no distant time. On the right, on the left hand side, we have that t is equal to 2 pi, okay, L to the power of half. Then there is another law that we need to apply right here. So what is the law? The law says it's actually called a power of a product rule. Power of a product rule. It says whenever you have something like a, b, c to the power of n, this n could be 1, it could be 2, it could be anything. Since they are multiplying inside the bracket, you are safe to distribute the powers, okay? So the n goes to the a, goes to the b, it also goes to the c. And this is now going to be a to the power of n, b to the power of n, c to the power of n, okay? It only works when they are multiplying. Like if you look at this bracket right now, the m multiplies the s. So we are safe to distribute the power, okay? But in a situation whereby they are adding up, for example, let's say we have a plus b, okay, all squared. This is not equal. It cannot be written as a squared plus b squared. Please take note, because they are not multiplying, they're just adding up. All right. So at this point right now, we can just go ahead and substitute their dimensions. Okay. So here we have our, this one is meters. Okay. Remember that it's meters per second square. And the SI unit for meters is capital letter L, which is length. Then this is multiplied by, for the second, remember that the SI unit for time is second, and the dimension for time is capital letter T. Okay, we determined that initially, and it's T raised to the power negative 2, and then outside the bracket, we still have our negative 1 over 2 outside. Okay, now correct. So I'm now going to replace again this L here. Remember that this L here refers to the length, and the dimension for the length is capital letter L. Hence, we're now going to have T is equal to 2 pi, then multiply by L. Please raise it to the power of half, because the L already has the power of half on top of it. And then this is now going to be 1, okay, over 2. 1 over 2. And here we have times. Let's now distribute. So since they are multiplying, this negative half goes to the L. It also goes to the T. Okay? Now here we're going to have L raised to the power negative half, negative 1 over 2, and then multiply by, so here we have T, okay, negative 2. Now this is not going to be, remember I said you have to distribute the powers, okay? Now this is not going to be negative 1 over 2 times negative 2. You have negative 1 over 2 times negative 2, okay? Correct. So we've distributed the power that is outside across everything inside the bracket. And now we have T is equal to 2 pi, okay? So there is another law that you need to know. And what is that law? Before I simplify this part, let's work on this right now, okay? So it's called the multiplication law of exponents. It says if you have something like a squared times, let's say a to the power of 3. When you have two like bases that are multiplying, okay? For example, a is a base, this a is a base, and the next a is also a base. Since they are the same and they are multiplying, you simply add their powers, right? This is now going to be a raised to the power 2 plus 3. And this is a to the power of 5, okay? So it says that whenever two like bases, for example, L is a base, L is also a base, they have been raised to a particular power. And whenever you have two like bases that are multiplying, you have to apply the multiplication law of exponents by adding their powers. Hence, this is not going to be L, okay, to the power 1 over 2, then plus negative 1 over 2. All right? So we've added the powers. Now, the next thing that we're going to do right now is to work on the t. For the t here, we have negative 2 times negative half. Okay? So let's now do that. We have a t here. So negative 2 times negative 1 gives you a 2. Okay, a positive 2 over 2. All right? So here we have t is equal to 2 pi. In case you're confused on how the negatives disappeared, please note that this negative 2 can be written as negative 2 over 1. Okay? So you multiply numerator for numerator, denominator for denominator. So negative 2 times negative 1 gives you a 2, and then 1 times 2 gives you a 2. Okay? Now let's continue. Right here we have L. Okay? So a positive times a negative gives you a negative, hence we shall have 1 over 2 minus 1 over 2. Okay? and we're also left with our t. Correct. So 2 divided by 2 gives you a 1, and on the left we have a t is equal to 2 pi. So half minus half, or 1 over 2 minus 1 over 2, give you a 0. This now becomes L to the power of 0 multiplied by t to the power of 1. Now let's proceed. T is equal to 2 pi. Any number raised to the power of 0 apart from 0 is equal to 1. This now becomes 1 times t. Okay? Remember that when you raise a number to the power of 1, it's still going to be the same number. Okay, here we have t is equal to 2 pi. Then 1 times t gives you a t. Remember what I told us initially, that in dimensional analysis, these numbers are not considered because they are dimensionless. They have no dimension. In this case, we are going to delete or eliminate this 2 pi because it does not have any dimension. Therefore, we're going to be left with t is equal to t. Having arrived at this solution, you can see that the left-hand side is equal to the right. And that means that this equation is truly dimensionally consistent. Remember that numbers or constants are not considered because they have no dimensions. I believe you understood this explanation. If you have any questions, comments, or contributions, please feel free to reach out to me in the comment section, and I'll be right there waiting for you. See you in the next video, where we shall be solving more problems on dimensional analysis. See you and bye.